We are going to review the main ideas of this chapter, and we're going to look at several problems. So the first one is, looking at an equation, can you identify if it's exponential growth or decay? And once you do that, can you find the rate of growth or the rate of decay as a percent? So let's take a look at the first example. A times 1 minus 0.22 to the x. Well, if we figure out the ratio value right here, 1 minus 0.22 is like 100%, minus 22%, which would leave us with 78%. So another way to write this is y equals a times 0.78 to the x. In this chapter, we looked at this ratio value, the base of the exponent. If this number is less than 1, then it's decay, and 78% is less than 100%. So we would say that this is decay. And we could say it's decay by 22%. If we take a look at the next one, a times 1.05 to the x. 1.05 is bigger than 1. It's 5% bigger than 1. So we're going to say this is growth by 5%. So really, you look at the 1. If it's bigger than 1, however much bigger it is than 1, that's the growth rate. And for decay, you look at what's being subtracted from the 1, and that's what it's going down by. Let's look at identifying different parts of the equation. Let's say your parents bought a car in 2010 for $14,500. The value of the car decreased by 12% annually, which means each year. Describe and correct the error in writing a function that models the value of the car since 2010. Justify your reasoning. So this problem is saying is they wrote a model here, but it's wrong. So what's wrong about it? So if we take a look at this model right here, the first number should be the starting value, and it is. So this is correct. This is the starting value in 2010. The next thing should be, how much is your car decreasing by? And if it's decreasing by 12% a year, the correct way to write this is 1 minus 0.12. What this is saying is your car is worth 12% of what it was the year before, but really, if we take 1 minus 0.12, this is saying our car is worth 88% of the year before, which makes more sense here. It's not going to be only worth 12% of the year before. So here's the error right here. It should be 1 minus 0.12. X would be the number of years since 2010, since you bought the car. Okay, so here's the error. Let's look at some word problems. The number of bacteria present in a laboratory sample after t days can be represented by the equation B equals 20 times 3 to the t. What is the initial number of bacteria present in the sample? That would be the number that's not the base of the exponent. So here it would be 20 bacteria. The 3 means that the number of bacteria is tripling every day. This is how you spell tripling. So again, the number of bacteria will be tripling each day. A giraffe population grew in the following pattern: 3, 9, 27, 81. If all the giraffes live and the pattern continues, how many giraffes will there be in the 7th generation? Well, if you take a look at these numbers, they should look familiar. When we did the exponent unit, we looked at numbers of different base, and these are all base 3. So I'm going to make a table so we can see generation. And this will be number of giraffes. Oops, that line's really crooked. Let's use the line tool. Okay. Okay, so in the first generation, the number of giraffes is 3. In the second generation, it's 9. In the third generation, 27. In the fourth generation, it's 81. Another way to write this is 3 to the first power, 3 to the second, 3 to the third, 3 to the fourth. So in the 7th generation, there would be 3 to the 7th giraffes. And if we put that in our calculator, that would be 2,187 giraffes. We've also taken some time to look at the table and the graph of an exponential. Fill in the following table below for the function y equals 5 to the x, then graph the function. Okay, so the first one, y equals 5 to the negative 2. We know from the exponent unit, this is the same as 1 over 5 squared, which is 1 over 25. If we change that to a decimal, that would be 0.04. The next one is y equals 5 to the negative 1, which is y equals 1 over 5 to the first power, which if we change to a decimal is 0.2. The next one's 5 to the 0 power, if you remember from the exponent unit. Anything to the 0 power is 1. The next one is 5 to the first power, which is 5. And then 5 squared is 25. So again, this right here would be 5 squared. Okay, let's graph that right here. I should have cut this off so low. Okay, so the first one was negative 2.4 is going to be like right here. Negative 1.2 is just slightly above. 0, 1, 1, 5. Oops. 0, 1. This is 5 right here, so 0, 1's right here. 1, 5. 2 jumps all the way to 25. So if we graph this exponential, you can see that it grows pretty quickly here. All right. Last one, how to read the graph of an exponential. How long does it take for the population to double from 500 to 1,000? All right, let's find 500 first. I'm going to draw a line over and down. So I would say this is about 25 years right here, so maybe 23 years. Your 23 is 500. How about 1,000? So I'm going to go over. My other lines seem crooked. And down. And again, I'm just estimating off my graph. If this is about 35, that looks like about 33 years. So from 23 to 33 years, it takes about 10 years. All right, here for the population to double from 500 to 1,000 if the growth rate is at 7% per year. So these are all the types of problems that we've been looking at this chapter. Your assignment, you will practice these types of problems.